Hello, this is Calculus 1, just in time 1, all the trig you need to know for Calc 1. First of the review lectures, my name is Scott Grizzard. So there are a couple really big ideas here, okay? The first really big idea is that trig is about a distance, not angles. So throw the angle stuff out of the window for the moment. You can talk about angles, but it's really about distance. So let's look at a sort of problem here. Okay. I have a circular racetrack. Okay. And it's a circular racetrack built around a football field that's in the middle. And the football field is, of course, 100 yards long, plus you've got both end zones. Then you might have some, seating here, some seating here. There's a vendor here and whatever. And then we're going to build a running track around it. Now, because we have all this stuff, the diameter of the racetrack is 200 yards. So the radius of the circle formed by the racetrack on the inside here is 100 yards. Now, this is what I mean when trig is about distance. The important thing is this 100 yards or one football field length, which I just called a field. Okay. The question is, what is the length of the track around the circle? How far, if this runner is running, how far is this runner going to run if the runner goes all the way around the track once? Okay. So that's a question. What's the circumference of the circle if my radius is 100 yards? So if you'll recall, C equals 2 pi r. The circumference of the circle is 2 times pi times its radius. So in this case, this running track, this runner is going to run, if the runner starts here, where it says start, and then runs around the track, runs all the way around the track, when the runner gets back to the beginning, the runner will have run 628 yards, about a little bit more than 628 yards all the way around the track. Okay, that's the first idea. It's about distance. So throw all that angle stuff out. We have a track here, and it's 628 yards all the way around, or 200 times pi. Now, let's suppose the runner's running, and we have a water boy sitting in the middle of the track. And the water boy's a little strained.
Bobby, you don't have what they call the social skills.
The water boy is right there in the middle of the track. Now, a normal person, to deliver water to the runner when the runner is right here, water boy's coming from the center. A normal person would just run like this, but the water boy's a little strange. The water boy is going to run like a taxi cab. He is only going to run east and then north, or east and then south, or west and then north, or west and then south. The taxi cab goes east and then north. Okay? The water boy is the same way. He runs east and then north. So, if the runner is right here, how far is the water boy going to go? The water boy always starts in the center. How far is the water boy going to go to deliver water to the runner? The water boy is going to go first east and then north. Now, note that this right here is 100 yards. That's the radius. But the water boy's a little strange. He's not going to walk the 100 yards. He's going to walk further. He's going to walk east and then north. So the question is, how far does the water boy go? So, if my runner is standing at the beginning, okay, when the runner is here, the runner has run 0 yards. Okay, so now, how far from the center of the circle is the water boy going to go east and how far north? So the eastiness of the runner here is 100 yards. And then what's the runner's northiness? Well, in order for the water boy to get to the runner, the water boy right now is only going to go east and north. Well, notice here that the water boy is just going to go east. Okay? The water boy does not need to go any north. He just goes straight east. Okay? So he's got, right now the water boy is going to go 100 yards east and no north. And that's one field and 0 fields. Because remember, one field is 100 yards. Now we have the runner, and we're going to let the runner run a quarter of the circle. So the runner is here. Now, the first question, how far does the runner run? Well, right now, the whole track, if we recall, is 628 yards. So the runner has run 1/4 of that length. The question is, how far does the water boy go east? And how far does the water boy go north? Well, the water boy is going to go 0 east. And the northiness, well, how far north is the water boy going to go? Well, he's going to go 100 yards. Okay. Well, let's suppose that the runner now runs half the circle. So the runner has run 314 yards. Okay. Now, the water boy, again, he runs east. The water boy goes east first and then goes north. Well, here, the water boy isn't going to run any east, correct? He's going to run west. Well, he's going to run 100 yards west. But west is really negative eastiness, right? So we're going to say that he's going to run negative 100 yards east. Is negative 100 yards. And my northiness is 0. Now that's 4.71 fields. So the distance here around the circle that we've run is 471. Now, again, we had eastiness is going to be 0. So our northiness here is going to be negative 100 yards. And now the water boy, again, we're back at the start. The water boy is going to go 100 yards east and no north. All right, so there's the idea, the big idea. Now, what about these ones in the middle? Well, those we're just going to have to figure out with a little bit of cleverness. So what happens if the runner runs here? So the runner has now run 1/4, half of this quarter, right? It's run 1/8. First of all, how far has the runner run? All right. So how am I going to figure out what the east and north is? Well, I've got a little bit of help here. I know that here I've got a triangle, and I know this length is 100 yards, or 1 football field. Okay? Now, I don't know these side lengths, but I do know something about these side lengths. I do know that this is halfway of the 90-degree angle, right? I know that this whole angle is 90 degrees, so that means that this right here is a 45-degree angle. And I know that this is a 90-degree angle, and I know that the sum of these angles must add up to 180 degrees. So that means that this angle must also be a 45-degree angle. So what I have is a triangle with a right angle at the top with two sides that are 45, with these two angles are 45 degrees. I don't know much, but so I know that this triangle is isosceles. This side, because this angle is equal to this angle, this side must be equal to that side. This is also a right triangle. And what's the most famous theorem in mathematics? Well, the most famous theorem in mathematics is the Pythagorean theorem, right? This is A, this is B, and this is C. So I know that A squared plus B squared equals C squared. And I know that A and B are equal. I know that this is isosceles. Well, because I know those two things, I know that A squared plus A squared, because A equals B, equals C squared. And I know that C squared equals, and C equals one field. Or 100 yards, or one field. So I know that A squared plus A squared equals 1 squared. Which implies that 2A squared equals 1. Which implies that A squared equals 1/2. Which implies, because I'm only dealing with positive numbers, this implies that A equals the square root of 1/2. Which implies that B equals the square root of 1/2 because A equaled B. So now I know that if this runner runs halfway from here to here, the water boy is going to go right, is going to go east, square root of 1/2, and north, square root of 1/2. Fields. So, believe it or not, that's all trig is. I want to know the northiness and I want to know the eastiness around this circle. That's all that the sine and cosine functions are. So, summarize. In other words, sine is north. S-I-N stands for. So, our big idea is that sine is north. It's all you need to remember. And then cosine is east. Okay? So, when our runner is standing here, remember our northiness was 0 and our eastiness is 100 yards or one field. So, and the runner here has run 0. Okay? So, when we've run 0, our northiness is 0. We're not any north. And our eastiness is 1. Okay, so forget all this stuff about, oh, it's, the y value is sine. No, sine is north. Not the y value, not the x value. Sine is north. Okay, now, when the runner has, let's look at what happens when the runner has run the quarter of the circle. Well, the circumference is 2 pi field, so a quarter of the circle is pi over 2. The northiness is 1, and the eastiness is 0. Well, let's keep going. Let's say that the runner runs here. The runner's now run half the circle. And as I'm saying, don't remember sine and cosine. Remember north and east. Every time you look at cosine, say, oh, that's east. And every time you see sine, sine is north. The eastiness, again, is 0. The northiness is -1. Okay. So we've got sine of 2 pi equals 0. The northiness of our runner now is 0. And the eastiness of our runner is now 1. And again, trig is about distance and sine is north. Okay, so What about our other little thing? What about when we went the quarter of the pi? This is all filled up. Let's make a new one. Oh, not a quarter of the pi, the half of the quarter. What happens when we are up here again? Okay, well, same proof we had before. The halfway of the quarter circle. Okay, so that is pi over 4. Now, from our previous proof, our eastiness is the square root of 1/2, and our northiness is the square root of 1/2. Okay, so you're probably going, oh, but wait, I remember from pre-calc that the sine of pi over 4 is square root of 2 over 2. I hate that. I really hate that. Let me show you where that comes from, okay? So what they've done is they've said, okay, they got the square root of 1 over 2, and that equals the square root of 1 over the square root of 2, which equals 1 over the square root of 2. And then, because I've got 1 over the square root of 2, I'm going to multiply by the square root of 2 over the square root of 2, because I don't want the square root on the bottom. Because calculators were never invented, and we're still looking up these things on tables. So we're going to do, okay, well, that's the square 1 times the square root of 2 over the square root of 2 times the square root of 2, and we're going to get the square root of 2 over 2. And that's where that comes from, and that is crap. Who cares? This is silly answer you memorize, and I hate it. This is bad. I hate these things. I hate these things. I hate these things. Just do a big on this thing. I don't like the fact that this is there. Okay? This is the better answer. This right here is an answer you understand. This right here is something you memorize. Who cares? This tells you nothing. This does not suggest at all where it came from. The square root of 1/2, that's interesting. That says, wait a minute. I know the Pythagorean theorem that the square root of 1/2 squared plus the square root of 1/2 squared equals 1. And that's interesting. This is awful, boring, don't care. So again, silly answer you memorize, don't want to know it. This is the much more interesting answer. That is the answer I am interested in. The square root of 1/2, not root 2 over 2. Forget about root 2 over 2. It's the square root of 1/2. And that is sine and cosine. Now, if you want to do something very interesting, you can head over to the internet, and there's this great site called mathisfun.com. And on mathisfun.com, they have this cool interactive unit circle. So here we are right now at 1 here. My eastiness is 1. I'm sorry, it's 0. If I've run 0, my eastiness is 1 and my northiness is 0. If I run pi over 4, my eastiness is 0.707 and my northiness is 0.707, which is the square root of 1/2. Okay. Likewise here, when I run here, my northiness is now 1 and my eastiness is 0. And so on and so on and so forth. And of course, the question is, what is this line going out here? What about this other line? What's this thing sticking out in here? Let's turn to that. Okay, so let's talk about what that line was. This is Desmos, which is a graphing website, which we will use several times during the class. And here I've got this is the circle here. And now I've got this is my runner here. And this is the path, the length of the path that the runner has run. Okay, so again, when we are here, the northiness is 1 and the eastiness is 0. But let's talk about what that line was. Here's the line tangent to the circle at my point. So if the runner has run 0.876, this red line here is the line tangent to the circle. The line tangent to the circle at that point. That's that. So the question becomes, what's the tangent function? The tangent function actually measures something about this line. The tangent function measures the distance from the point, from the runner, back to this x-axis. And that's what the tangent is. It is a function about this line, about this picture. So the tangent is the length of that line. So if we go back to our interactive unit circle, you'll see where it's got the tangent sitting there at 9.995. You're going to get 1.54. That's the length of the line from this point over to the x-axis. So that is the length of the line from here to here. And that's what the tangent actually is. It's not sine over cosine. It equals that, but that's not what it is. It is the length of this line. To see why, we need to return to our unit circle. So here's our unit circle. And here's, again, I took away this is the tangent line here. Bring that back. There's the tangent line, and I've highlighted the section we're interested in. So this is the tangent. This right here is the eastiness, the cosine. And this right here is the northiness, or the sine. This right here is the radius, and I've also added a line that passes through the point that extends the radius. Okay, so I've got the tangent line here, the perpendicular line here, or the normal line it's also called. But the point is that it extends the radius. And then I've got this is the section I'm interested in, the tangent. And this right here, the radius, the cosine, and the sine. And this is my arc length right there. Now, the setup here, what we're going to do is we want to talk about these triangles. Notice that there's a triangle here, and there's a triangle here. And they share that angle. So let's look at that. Okay, let's make some notes here. So the arc length is theta. This length right here is the tangent of theta. This right here is the eastiness. We can get rid of the notes. This right here is the eastiness. And this right here is the northiness. This length right here is 1. They've got two right triangles. This one's right, and then this larger triangle here. And notice that they share an angle. They share that angle there. I don't know what it is in degrees. I actually do. I can compute it based on the arc length of theta. I can compute the degrees. But I don't care specifically what they are. What I care about is that this is a right triangle. And I know one of the angles is shared between both triangles. So what I care about is this. I'm going to call this one beta. And then it's shared between this other triangle. And this other triangle is also a right triangle. This is a right triangle. This base here is the secant, in case you care, but we don't. This right here is the tangent. And since they share an angle, we'll call this angle gamma. They don't share this angle, but notice that that angle has to be equal. They have to be equal because 90 plus alpha plus beta equals 180. And 90 plus alpha plus gamma equals 180. So I know that beta has to equal gamma. They're not the exact same angle, but they're equal to each other. The angles are equal, even though they're in different parts of the triangle. That means what I have are two similar triangles. And so I can actually illustrate this a little bit more. What I'm going to do here is, let's get rid of some of this extra stuff. This line angle right here, they share this angle. So I can preserve this angle by simply flipping the triangle. So what I'm going to do is I'm going to flip this so that this is now here. So all I'm doing, I'm going to have the exact same angle, and I'm going to use the exact same length. So the length from here to here is going to be equal to the length from here to here. So all I'm doing is I'm flipping the triangle, kind of along this kind of line here. So let's do that. So all I've done is I've flipped the triangle. And if you can't see that, just think about this triangle just going here. Just think about me taking this gamma angle that I've got and just kind of dragging it across and kind of pulling it up. So I haven't changed this side. I've just kind of flipped it up. Okay? So that it's now standing on the radius, because this right here is the radius and it is still 1, and I've still preserved this angle. So my radius down here, this right here, which was on the old triangle, that side is whose length was 1, I knew that, became this side, whose length is now 1. And so because I preserved that side, I've also preserved this. So what have I done? Well, now I've got similar right triangles. That means that the ratio, and if you recall from high school geometry, and you may have, blocked this out for the sake of your sanity, and that's okay. I certainly understand that. Let's go ahead and paste this in here. Okay. So this is the base. Oops. So its new base is 1. This is still, all I did was flipped it. I preserved the length of this side. All I did was flip it. So this right here is still the tangent. Its length is the tangent. It's not the actual, right? The actual tangent goes here, but this is the same length. This right here is the cosine. This right here is the sine. This right here was my alpha that they both shared. This is the right angle for that one. That's the right angle for that one. I've got two similar right triangles. Okay. That means that the ratios of their sides are the same. In other words, I'm going to call the cosine here, this is the A, I'm just going to call this the A side. So this is going to be the A1. This right here will be the B side for the first triangle, and this larger side will be A2, and this one right here will be B2. So the ratios of the A side over the B side, I want the B side over the A side, don't I? So the ratios of the two sides are equal. That means that the sine right, the B side, the B over A, the B over A1, B1 over A1, and B2 over A2 must be equal. So sine over cosine actually equals tangent over 1. And that's the proof. Okay, so what were the big ideas? There's the first one. It's about distance. Two, SIN stands for sine is north. Right? SIN stands for sine is north. So remember that sine is the northiness. You need to know that that tangent function measures a distance, and which distance that is. Right? And you need to remember that sine over cosine equaling tangent, that's actually a theorem. You have to prove it. I mean, you don't have to prove it, but it has to be proven. It's not just that it is that. It equals that, but it's not that it is that. Okay? It is that line. So I highly encourage you to remember this diagram because we're going to use it again. We're actually going to use it a couple of times in this class. It's a nice diagram, and it's what these things are. That's the actual cosine. The eastiness is the cosine. The northiness is the sine, and the tangent is the length of the line segment from here to here along the tangent line. So it's this line here. If I take the radius and I do a perpendicular angle, right? If I do a 90-degree right angle, there it is. And notice how it only touches the circle once. And we're going to come back to that. We're going to generalize this idea of tangent lines, and we're going to come back to this diagram. So that's what I have for you. Good evening.